On the board right now, we see 3 examples of acceleration time graphs. What would be our manipulated variable in these graphs? 3 graphs you've never seen before. Our manipulated variable in all 3 cases would be time, because it's on the x-axis. Acceleration would be the responding variable. It's on the y-axis. Good. Remember, the title is always y-axis versus x-axis as well. Can you tell me what this first graph represents here? Don't get it mixed up with your position time graph that had the same shape or your velocity time graph that had the same shape. You guys know if the x-axis or the y-axis, either one of those changes, then you guys know that the significance of it is going to be different. What does this mean as compared to a position time graph or velocity time graph? No, it's not showing the acceleration. It's not showing the rate of acceleration. Be careful with that, though. You might be thinking the right thing. You're not saying it right, though. Kyle? Okay, it's showing the acceleration over time, but what's happening to the acceleration over time? It's what? Yeah, for the first graph. Jen, what's happening to the acceleration over time there? Good, good. Not only is the position changing, not only is the velocity changing, or the velocity is increasing, that velocity increases when it accelerates, right? But the acceleration itself is increasing. So we're going to call that an increasing acceleration. This would be that situation where you're driving your car, you put your foot on the accelerator, on the gas pedal, and you speed up a little bit. You accelerate. But then you put your foot down further, and not only are you speeding up, but the rate at which you speed up is increasing. So you're speeding up quicker. That's what we've got here. Okay? Increasing velocity, but also the rate at which your velocity increases is increasing. Now, if I was to plot this as a velocity time graph, what do you think it would look like? If I wanted a velocity time graph to represent the same thing as this acceleration time graph, what shape would it have to take up? It would have to be curving upwards, yes. Okay, so a straight line on that v versus t graph would show acceleration, but a curved line shows increasing acceleration, which is exactly what we have here. Okay, let's take a look at the next one here. Acceleration versus time, we're flatlining here this time. Nice flat horizontal line. What does this represent? Yep. Yeah, it's accelerating, it's speeding up, but it's a constant rate of acceleration. So this is putting your foot on the accelerator, on the gas pedal, and keeping it in the same place. You're speeding up, but you're speeding up at the same rate the whole time. We're going to say constant or uniform acceleration. Now, if I was to plot that as a velocity time graph to try to get the same meaning of it, or the same significance from it, what would it look like? Yep. Yeah. Yeah, that would be the straight line sloping upwards, right? Uniform or constant acceleration. And finally, this last one, what's going on here? This one confuses people sometimes, actually. What is it? Good. You said it perfectly. Decreasing acceleration. This is not, contrary to what a lot of people will tend to think, this is not deceleration. What's happening here? Look, at the beginning, the acceleration is high. At the end, the acceleration is lower. But there's still an acceleration, right? We're still speeding up at the end of the problem. We're just not speeding up as quickly as we were at the beginning of the problem. If you go back to the gas pedal analogy again for a second, this would be putting your foot on the gas pedal right down to the floor, like right down to the floor to start off. You accelerate really, really quickly, and then you kind of ease off a bit. You're still speeding up, but you're not speeding up as quickly as you were before. Now, if I was to turn that into a velocity time graph, what would the shape of it be? You're accelerating, but the rate at which you're accelerating is decreasing. So you're speeding up, but you're not speeding up as quickly as you were before. Brogan? Yeah, it's the curved one like this. So it's, you see here that the velocity is increasing the whole time, but the velocity is not increasing as quickly towards the end of the graph as it was at the beginning of the graph. All right? You're responsible for all three of these, but only shapes, no mathematics, unlike the position time graphs and the velocity time graphs, where we have to know the shapes and we have to be able to do calculations with those.